want to begin by thanking the group of tutors who worked with me a few summers ago in studying Jane Marcet. We had a lot of fun together. I think there was one shattered glass beaker and some fire. Mr. Coleman maybe was responsible. I'd also like to thank the librarians. They've been able to pull Jane Marcet off of our shelves for us. We have not the first edition, but maybe one of the first few editions in the library. It's very fragile, and they're putting it on display. So if you want to go over there and take a look at it, I would encourage you to do so. I'd also like just to give a shout out to the Othmer Library in Philadelphia. They have a really great collection of chemistry textbooks, or just chemistry books in general, and a lot of them are available to view online, and I've been able to email them, and they'll get me photocopies of books that I don't have, the resources to go up there myself and look at. So yeah, that's been fantastic. Okay. Jane Marcet's Conversations on Chemistry is among the earliest introductions to chemistry after Antoine Lavoisier standardized chemical nomenclature. Her work is a theoretical introduction to chemistry, but it is also a conversation between three women having a lot of fun in a laboratory. The book is filled with wonder, careful reasoning based on observations of nature, and humor. I've found myself laughing out loud on numerous occasions. In her descriptions of how tannins affect animal skin, Marcet explains how the bark of oak trees is broken up and put in barrels of water in which the animal skins sit. They then go on to discuss other sources of tannin, including wine, at which point Caroline makes the following hypothesis. One might suppose that men who drink large quantities of red wine stand a chance of having the coats of their stomachs converted into leather. As with all dialogues, there have been guesses about the names that Marcet gives her women: Mrs. B, Caroline, and Emily. Mrs. B, in our conversations, is as authoritative as Jane Marcet is meek in her preface. This alter ego is often supposed to be a reference to Margaret Bryan, a natural philosopher who ran a school where she taught astronomy and physics to women. The students are Caroline and Emily, young women who have already completed a course of study with Mrs. B on Newtonian mechanics, optics, and astronomy. The images here are drawn from their study of optics in conversations on natural philosophy. And we'll have reason to look at one of them tonight. Caroline is imaginative, but sometimes forgetful, and maybe a bit flighty. Generally, scholars seem to dismiss her as less serious, and attention goes to Emily. One scholar suggests that Emily might be a feminization of Rousseau's Emile. I actually think both students are excellent. Caroline touches things before she is invited, and is more inclined to get messy, plunge her hands into the mercury, burn herself with muriatic acid, and she asks wonderfully impertinent questions. Emily is more timid, needs to be invited before she touches anything, but she has a better memory, is better at analysis, hypothesis making, and counter-arguments. I think there is textual evidence to support the idea that Caroline and Emily are actually named after two famous philosophers of Marcet's time: Caroline Herschel, a German astronomer, and Émilie du Châtelet, a French natural philosopher whose translation of Newton into French is still used today. The lecture will have roughly equal parts. In the first half, we will look at Marcet's theory of caloric, in particular her theory of free caloric. I've subdivided this part of the lecture by the questions that the women investigate and the experiments that they conduct. I'll just try to make these subdivisions clear as they happen. In the second half, I will talk about what we can learn from Marcet's work as a whole. We will begin by considering the question, what is caloric? The discussion of heat will take up 3 consecutive conversations. It's about 150 pages. And in fact, the conversation doesn't end there. So it goes for basically 700 pages. There is not a single chemical process that does not require special attention to heat. But before we turn to Mrs. B's definitions for caloric, we should briefly consider an early experiment on natural light. In this experiment, Mrs. B describes sunlight passing through a prism and being refracted. In addition to a brilliant array of colors, there's a strange hot spot on the side of the red light outside the visible range. She concludes that two agents were emitted in the rays of the sun and that heat was less refrangible than light. So she doesn't give a diagram of this in Conversations on Chemistry, but we do have some from Conversations on Natural Philosophy. So if you guys see this one right here, so we have light coming through a prism, and there's no way you can read these words, but it's just the different colors of the spectrum. So down here is the red light, which is, as you can see, is least refracted. It's the closest to going straight. On the side of the red light over here is a hot spot. Mrs. B then adds to this strange phenomenon. At a distance away from the blue light, there seems to be invisible rays that have the chemical effect of separating oxygen from bodies. So right up here, beyond, again, the visible spectrum, there seems to be some invisible rays that have the power, if you were to shine them on, rust or something, the oxygen would go away. I guess I'll keep it vague right now, and then the metal would remain. The array of visible light is bookended. So this array of visible light is bookended by rays of warmth on one end and invisible rays that separate oxygen from bodies on the other. The prism, then, has taken something that Marcet herself has named a simple, imponderable agent, light, and shown that it has three separable powers: the chemical power to separate oxygen, the power to illuminate, and the power to heat. One cause seems to have here three effects. The prism experiment serves as a backdrop to their conversation on heat. Is there a fundamental relation of light to heat? Is one cause the other effect? Does heat itself have a multitude of effects like light? Against this backdrop, Mrs. B begins explaining the origin of the term caloric. It was in order, quote, "It was in order to avoid the confusion which arose from thus confounding the cause and effect that modern chemists adopted the new word caloric to denote the principle which produces heat." She then emphasizes this point, saying that heat, strictly speaking, is the sensation produced by caloric on animated bodies. This word, therefore, in the accurate language of science, should be confined to express the sensation. By distinguishing cause from effect and caloric from heat, Mrs. B is now able to introduce, at least partly, a further distinction to Caroline and Emily, that between free caloric and combined caloric. Free caloric comprehends all heat which is perceptible to the senses and affects the thermometer. Free caloric, then, is more closely aligned with a phenomenon of heat than combined caloric. When Caroline asks for further clarification on the nature of combined caloric, Mrs. B says that she will have to wait. For now, it is defined by what it is not. It is neither sensible, nor does it affect the thermometer. Mrs. B uses the word free to mean two things: free motion and free of body. For this reason, Mrs. B gives at the outset a synonym for free caloric: radiant caloric. By using radiant caloric, Mrs. B calls to mind a likeness between light and caloric. But before she develops this likeness, Mrs. B will return to more traditional accounts of caloric. Fluid caloric. If you heat something up, it expands. In Marcet's language, free caloric causes bodies to dilate. Here is Mrs. B. So I'm going to be reading the dialogue now. I'll read Mrs. B and Emily and Mrs. B. I might do what Mr. Lasell did and dance around a little on stage. Mrs. B. One of the most remarkable properties of free caloric is its power of dilating bodies. This fluid is so extremely subtle that it enters and pervades all bodies whatever, forces itself between their particles, and not only separates them, but frequently drives them asunder to a considerable distance from each other. It is thus that caloric dilates or expands a body so as to make it occupy a greater space than it did before. This is Emily. I guess I can't do that, can I? Emily. The effect it has on bodies, therefore, is directly contrary to that of the attraction of cohesion. The one draws the particles together, the other drives them asunder. Mrs. B. Precisely. There is a continual struggle between the attraction of aggregation and the expansive power of caloric. And from the action of these two opposite forces result all the various forms of matter or degrees of consistency, from the solid to the liquid and aeriform state. And accordingly, we find that most bodies are capable of passing from one of these forms to the other merely in consequence of their receiving different quantities of caloric. In this passage, Mrs. B seems to be suggesting that the opposing forces of attraction and expansion create both bodily extension and solidity. Without caloric, attractive forces might cause the collapse of all bodies. The power of caloric to dilate bodies also gives us a way of detecting and measuring it. Marcet will discuss a number of different kinds of thermometers. I guess I can take this out. Maybe just from here. So these are traditional thermometers at the end. You'll have a liquid in a bulb. You submerge the bulb into, let's say, a beaker that you want to measure, and the liquid will climb. I think these two end up being water and spirit of wine, as she calls it. This one is one that you probably aren't familiar with. This stick right here that starts at A and goes to there has been heated. It's actually being heated by these little flames that are underneath it. And as it's heated, you can see the iron bar expand. And as it expands, it pushes this, and then there's some gears here. And these gears multiply the expansion. They talk about that. And then the needle will move to measure how much it's expanded by. This is called a pyrometer, which I think is kind of neat. Here is a traditional thermometer. You guys are probably familiar with it. Marcet will talk about the different scales and some of the mistakes that were made in creating those scales. So for example, the reason why we have 32 degrees as the freezing point is because Fahrenheit thought that water with ice was the coldest thing possible and set that as a 0 point. And then this thermometer right here is a differential thermometer, and we're going to talk about that more. So I've zoomed in on that one. Here's the differential thermometer. One of the most sensitive thermometers is the differential thermometer. This thermometer is also a paradigmatic thermometer because its physical form embodies the hidden theoretical form of all thermometers. Here's Mrs. B. I'm going to do a longish passage. Mrs. B. I can show you an air thermometer of a very peculiar construction, which is remarkably well adapted for some chemical experiments, as it is equally delicate and accurate in its indications. Caroline. It looks like a double thermometer reversed, the tube being bent and having a large bulb at the end of each of its extremities. Emily. Why do you call it an air thermometer? The tube contains a colored liquid. So I don't know if you guys can see it, but there's sort of a solid line right there. That's the colored liquid. It goes up to about there. Mrs. B. But observe that the bulbs are filled with air, the liquid being confined to a portion of the tube and answering only the purpose of showing, by its motion in the tube, the comparative dilation or contraction of the air within the bulbs. This affords an indication of their relative temperature. Thus, if you heat the bulb A by the warmth of your hand, the fluid will rise towards the bulb B, and the contrary will happen if you reverse the experiment. But if, on the contrary, both tubes are of the same temperature, as is the case now, the colored liquid suffering an equal pressure on each side, no change of level takes place. Caroline, this instrument appears indeed uncommonly delicate. The fluid is set in motion by the mere approach of my hand. So here she is again, like just touching something before she's allowed to, or invited to. So one of the things I'm a little bit curious about is, Marcet makes it sound like there's sort of an equal distribution of the liquid, but she actually does have a scale on the picture that she includes, and the 0 point is here. I'm not sure if you guys can see it. I was trying to think through why this might be, and I assume in the construction of the thermometer, it's just incredibly difficult to get the gas and the liquid in the thermometer in just the right way before you close up the glass. So you kind of end up with the liquid where it ends up, and then the person constructing the thermometer has to label a certain point 0 degrees. I'd be kind of curious to hear what you guys think about how one would construct something like this. I haven't been able to figure it out. The gas in a branch of the thermometer dilates, causing it to push against the liquid indicator. Here, the extent of the effect, the degree of dilation of the gas, indicates something about the nature of the cause, the quantity of caloric that is in the gas bulb. But how does the quantity of caloric dilating the gas tell us anything about the quantity of caloric in the substance we are measuring? Here, Mrs. B continues. Let us compare a thermometer to a well, in which the water rises to different heights according as it is more or less supplied by the spring which feeds it. If the depth of the well is unfathomable, it must be impossible to know the absolute quantity of water it contains. Yet we can, with the greatest accuracy, measure the number of feet the water has risen or fallen in the well at any time, and consequently know the precise quantity of its increase or diminution, without having the least knowledge of the whole quantity of water it contains. Caroline, oh, now I comprehend it very well. Nothing appears to me to explain a thing so clearly as a comparison. Caroline, who's ever ready with a play on words, captures the theory behind the thermometer. It is making a comparison. As you are looking at this image of a differential thermometer, you might be struck with how like a balance it is. Or perhaps you might be thinking about how Mohs' scratch test for mineral hardness is a lot like this contest that has been set up between the gases in the bulbs. There are, I think, similarities worth dwelling on in both cases. But there's also something fundamentally different about the way in which a thermometer works from these devices. Let's return to Mrs. B's comparison with a well. Suppose I lower a bucket into a well and pull it out with 3 gallons of water in it. If I declared that the well had 3 gallons of water in it, that would be ludicrous. We need to take care that in interpreting the thermometer, we aren't making a similar mistake. When a thermometer is submerged, it is not simply scooping up a quantity of caloric. Instead, after a period of time, the beaker of water and the thermometer will take on the same quality. The thermometer will become like the beaker of water. I think this is pretty unique. I'd be curious if you guys have examples of measuring devices other than temperature where this happens. What is the quality that the thermometer and the beaker of water come to share? That becomes our question for the next section. In order to fully explain the thermometer, Mrs. B needs to introduce another property of free caloric to Caroline and Emily. Free caloric tends to diffuse itself equally. If this property be true, then the caloric in the beaker of water is diffusing itself so that the glass around the thermometer and the glass in the thermometer will eventually have an equal diffusion of caloric as the water that is being measured. Mrs. B continues to use this language of equal diffusion for a page or so before slipping and using the word equilibrium. Caroline, who's always mindful of their chemical nomenclature, doesn't let this go by without comment. Caroline, but why does caloric tend to an equilibrium? It cannot be on the same principle as other fluids, since it has no weight. So I think this is where the freshmen are right now, where we talk about equilibrium as if heat somehow had weight. Mrs. B, very true, Caroline, that is an excellent objection. But I know of no expression that would explain my meaning so well. You must consider it, however, in a figurative rather than a literal sense. Its strict meaning is an equal diffusion. We cannot indeed well say by what power it diffuses itself equally, though it is not surprising that it should go from the parts which have the most to those which have the least. The thermometer becomes like the thing it measures because caloric equally diffuses itself. Because the thermometer presents different measured I'm going to read this part slowly, it's a little tricky. Because the thermometer presents different measured bodies with the same quantity of thermometric material, each time this thermometer makes a measurement, the ratio of the quantities of caloric that it obtains on any two measurements will be proportionate to the ratio of the diffusion of the caloric in the materials measured. Hope that makes sense. But how does this caloric diffuse? While Mrs. B claims to be unable to say by what power it diffuses, she will have a lot to say about how it diffuses, how its motion takes place. She eagerly leaves aside the idea that caloric is a fluid, basically bye-bye Lavoisier, and that it reaches equilibrium, and instead turns to the idea of Professor Prevost and Professor Pictet of Geneva, who believe that caloric is best understood as radiating particles. This will be the first of 3 ways that she will introduce to the girls for the way in which caloric becomes equally diffused. This is radiating caloric. Here is the new theory of caloric that Mrs. B introduces to her students. Caloric is composed of particles, every one of which moves with a rapid velocity, such that there are rays or lines of these particles which move in every possible direction. Because of this radiating motion, caloric is universally diffused. It takes place in free space, so there need not be any bodies, and comes from bodies of every kind, so that all bodies, including you guys, are constantly radiating caloric, no matter how cold or warm they feel. Caroline and Emily are fairly good sports about this new theory, but finally Caroline breaks down. Mrs. B, I wish I could see these rays of caloric. I should then have greater faith in them. Eventually, Mrs. B confesses that she does have some experiment to show them. This one was originally put together by Professor Pictet. Mrs. B, I place an iron bullet about 2 inches in diameter and heated to a degree not sufficient to render it luminous, she'll talk about that later, in the focus of this large metallic concave mirror. So right here is a hot iron ball. The rays of heat which fall on this mirror, right there, so it's like a big parabolic mirror, are reflected agreeably to the property of concave mirrors in a parallel direction so as to fall on a similar mirror, which you see is placed opposite to the first. It's at the distance of about 10 feet. Thence, the rays converge to the focus of the second mirror, in which I place one of the bulbs of this thermometer. So here we're going to use the differential thermometer. Now observe in what manner it is affected by the caloric, which was reflected on it from the heated bulb. The air is dilated in the bulb, which we placed in the focus of the mirror, and the liquor rises considerably in the opposite leg. Emily: but wouldn't the same effect take place if the rays of caloric from the heated bullet fell directly on the thermometer without the assistance of the mirrors? Mrs. B: the effect would in that case be so trifling at the distance at which the bullet and the thermometer are from each other that it would be almost imperceptible. The mirrors, you know, greatly increase the effect by collecting a large quantity of rays into a focus. Place your hand in the focus of the mirror, and you will find it much hotter there than when you remove it nearer to the bullet. So I think she's asking Emily to put her hand right here and then move her hand towards the bullet. Emily: oh, that is very true. It appears extremely singular to feel the heat diminish in approaching the body from which it proceeds. Caroline: and the mirror, which produces so much heat by converging the rays, is itself quite cold. You'll notice here Caroline touched the mirror without being asked. Emily had to be asked to touch something. Pictet's parabolic mirror experiment, like the prism experiment, shows a close kinship between light and caloric. But whereas in the prism experiment we saw that light causes heat, here we see a paradigmatic case of a hot body, a hot iron bullet, emitting something that behaves like light. Like light, it can radiate from bodies and travel quickly through empty or nearly empty space, and it seems to follow the laws of optics. With the evidence of this experiment, Marcet feels that she is in a position to improve upon Lavoisier's idea that equilibrium is established through the settling of a subtle liquid, with the idea that equal diffusion is established through the rapid motion of calorific rays. Marcet, in other words, is replacing the mechanism by which equilibrium is established. Rather than it being established by something analogous to weight, it is established through a sort of averaging out of the motion of caloric through space. This experiment also shows us something about caloric that may help us better understand light. The mirrors reflect the caloric and, as Caroline notes, because she is always reaching out to touch things, don't seem to have absorbed any caloric. What about the thermometer? It clearly absorbs some of the caloric as the gas in the bulb at the focus expands, but the gas is just common air, the very air that the caloric rays seem to bypass between the two parabolic mirrors. And the glass, like the mirror, is very reflective. So how is it that this gas is expanding? Basically, we have a problem. It's like, how is the caloric getting inside the thermometer? It should just bounce off. Towards the close of the discussion of radiant caloric, Mrs. B will draw their attention to the way in which different materials absorb and emit radiant caloric. In this experiment, she takes a tin box, paints one side black, the next white, and covers a third with a plane of glass, and leaves the fourth side as it is, bare tin. She then fills the tin box with hot water and places it at the focus of the parabolic mirror where the iron bullet once stood. She begins with the black side facing the mirror. The branch of the differential thermometer at the other focus rises considerably. She then rotates the box so that the white face is towards the mirror and the thermometer falls. She then rotates it once more so that the glass is facing the mirror. It falls again. She rotates it one more time so that just the tin itself is facing the mirror and the thermometer reaches its lowest point. There's a lot to discuss in this experiment, but what I would like to draw your attention to is this. After reaching equilibrium, the glass must absorb and radiate just a little bit more caloric than the shiny tin. So however that thermometer is catching heat, the glass on the outside seems to do a better job than some other surfaces, though it's pretty bad actually at it. If we return to think about how the thermometer works, we can at least be sure that more caloric is absorbed by the surface of the glass than the parabolic mirrors. We also might wonder if the inside of the thermometer becomes something like a caloric trap, as if the insides of the cylinder were like the parabolic mirrors themselves. But even so, we're still left with a bit of a puzzle. How is it the gas itself takes up this free radiant caloric and expands? The radiant caloric is disembodied and free. How is it that it becomes part of the body? And in what way does it become part of a body while maintaining its freedom of movement? Conduction. While caloric might very well be both radiated and absorbed by all the bodies around us, something different seems to happen when you reach out and touch another body. In their conversations about conduction, Mrs. B, Caroline, and Emily walk around the room touching objects, much like we do in freshman lab. As they do so, Mrs. B explains that the objects in the room, which are all colder than they are, feel differently because of the rapidity with which caloric is conducted through various bodies. Conductivity, she says, is not strictly about how much caloric is passed on, but about the speed with which it moves. Through some materials, caloric finds a very easy passage. When Emily asks why, Mrs. B says this: "This is a point not well ascertained. It has been conjectured that a certain union or adherence takes place between caloric and the particles of the body through which it passes. If this adherence be strong, the body detains the heat and parts with it slowly and reluctantly. If slight, it propagates it freely and rapidly. The conducting power of a body is therefore inversely as its tendency to unite with caloric." Unfortunately, Caroline seems to have dozed off for a bit and not caught Mrs. B's use of the word heat in this passage. In the first and last sentence, Mrs. B speaks of a joining together of caloric and of body, but in the second sentence, she speaks of a strong adherence of body and caloric, which leads the body to detain heat. This is where she uses it. Mrs. B might be suggesting that the combination of body and caloric, if it is strong, is heat. A weaker combination, and the caloric seems to merely pass through the body freely and rapidly, perhaps without even heating the body. Emily asks, but what is the reason that some bodies are better conductors of heat than others? In response, Mrs. B introduces a number of examples which establish that density seems to be correlated with conductivity. Her examples include solids, fluids, and gases. Here, Mrs. B and Caroline conduct a very simple experiment to show that fluids of different densities have differences in conductivity. Mrs. B: "In fluids of different densities, the power of conducting heat varies no less remarkably. If you dip your hand into this vessel full of mercury, you will scarcely conceive that its temperature is not lower than that of the atmosphere." Caroline: "Indeed, I know not how to believe it. It feels so extremely cold. But we may easily ascertain its true temperature by the thermometer. It is really not colder than air. The apparent difference, then, is produced merely by the difference of the conducting power in mercury and in air." If conductivity is correlated with density, does this help us better understand the nature of the adherence between caloric and body? Are these observations compatible with Lavoisier's idea that caloric is a fluid, or with Pictet's idea that caloric is composed of radiating particles? Whether caloric is a fluid or radiating particles, if caloric fills the interstices between solid ponderous bodies, then both these ideas, I think, are incompatible with Mrs. B's observations about density. If I imagine that caloric passes through the sieve, either as a liquid or as fast-moving particles, the tighter the mesh, so the denser the body, the more the caloric will be detained by the body, and the more poorly it will be conducted. So the more dense the body, the caloric's just going to get stuck. If, however, I imagine that bodies are a series of interconnected pipes through which either liquid or radiating caloric might find passage, then the more pipes and the more connections between the pipes, that is, the denser the body, the more quickly the caloric will pass through. What seems to matter for explaining conductivity is not the nature of caloric, but the nature of the body and its way of combining with that caloric or leaving a passageway for the caloric. Throughout the discussion of the conduction of caloric, Mrs. B has made an important but subtle shift in language. Rather than talking about the power of caloric, Mrs. B shifts to speaking of the power of bodies to conduct it. Even though we are still talking about the motion of caloric and how it reaches a state of equal diffusion, the transitory union of body and caloric heat is more essentially about the state of matter that emerges from the union of body and caloric than it is about the power of caloric by itself. What this hints at, and what we are about to see play out, is that Marcet's initial distinction between free and combined caloric was not a distinction between entirely different species of caloric. Instead, she was presenting us with two ends of a spectrum: the freest and most radiant caloric, and the most tightly bound and encapsulated caloric, combined caloric. Agitation. After Caroline plunges her arms into the vessel of mercury, Mrs. B reflects on how little the sense of feeling is to be relied on as a test of the temperature of bodies. In fact, she will go on to say, one might even doubt whether fluid conducts caloric at all. This skepticism makes sense if we continue with the analogy introduced above. Bodies conduct because they provide a coherent pathway for the caloric to travel. A fluid body can't provide a coherent pathway. Fluids, Mrs. B explains, will allow for the movement of caloric, but they do so through agitation, or the movement of the bodies themselves. The caloric is no longer finding free passage through body. Instead, it attaches itself to bodies, which themselves move. These bodies move because, in becoming attached to caloric, they change. In fact, they become lighter and less dense, and once they are less dense, the denser bodies around them descend, pushing them up. To provide some evidence for this claim, Mrs. B will introduce an experiment conducted by Count Rumford. Mrs. B reports that he succeeded in making the upper surface of a vessel of water boil and evaporate while a cake of ice remained frozen at the bottom. As Caroline puts it, that is very extraordinary indeed. In this experiment, because the water at the top is boiling rather than the water at the bottom, no movement or current forms in the boiling water. The water simply evaporates from the top while the colder water remains resting on the ice below. Mrs. B says that, quote, Count Rumford hence infers that no alteration of temperature can take place in a fluid without an internal motion of its particles. And as this motion is produced only by the comparative levity of the heated particles, heat cannot be propagated downwards. Mrs. B does not conduct Count Rumford's extraordinary experiment for Emily and Caroline. Instead, she sprinkles, I'd be curious to think about why. Maybe it's just really dangerous, maybe it doesn't work. I don't know. Instead, she sprinkles some amber dust into a phial of water and then submerges the phial into a Florence flask of much hotter water. So we have like a little, this is the experiment we tried to do and broke glass, a small phial of water and some amber dust in it, and then we put it into a larger beaker of water that's hot. Emily and Caroline observed two currents in the inner phial, one rising along the sides of the phial and the other descending in the center. After showing Caroline and Emily this and related experiments, Mrs. B is surprisingly circumspect in her response to Count Rumford's claim that liquids do not conduct caloric. Though I believe that Count Rumford's theory as to heat being incapable of pervading fluids is not strictly correct, yet there is no doubt much truth in his observation that the communication is materially promoted by motions of the parts. Agitation is not the free radiant motion of caloric, nor is it body guiding caloric's motion as in conduction. Here again, Marcet subtly changes language. We do not see the phrase power of caloric here, nor do we see the phrase power of the body. Instead, we see repeated references to weight and levity. In other words, to the power of gravity. As caloric becomes deeply combined with body, it almost seems to abdicate its throne. Its power to move has somehow been subsumed by the powers of Newtonian forces. Does the sun warm the atmosphere? The abdication allows for the equal diffusion of caloric to occur on a much grander scale. Caroline asks the question, does the sun warm the atmosphere? And the surprising answer, at least it was surprising for me, is no. The power of the sun, the power of radiant caloric, is somehow insufficient to warm the air, or, as Mrs. B modifies the claim later in the conversation, the sun is too powerful to warm the air. There seems to be a disproportion in the power which allows the rays of the sun to simply pass through the atmosphere, and the power it takes to warm them. Instead, as Emily correctly anticipates, the earth itself plays an important role. The sun radiates caloric, which passes easily through the most transparent and sparsely bodied atmosphere, mostly transparent, in order to be absorbed by the earth. The earth radiates in turn, but its radiation, like that of the sun, is too powerful as well. Its rays pass back out through the atmosphere into space. If we expand our perspective, what one imagines is one very large, very hot body, and a second large body at a very great distance. On this grand scale, the cause of all heat is simply caloric radiation and absorption. If we return to Earth, we can now see that the warmed Earth is in fact in contact with a very thin strata of air which rests on its surface. These particles are warmed by the conduction of caloric. By gently touching the surface of the Earth, caloric passes through the body of the Earth to the body of these gases. These gases, unlike a conducting solid, retain the caloric and are transformed by it, becoming specifically lighter. Their increased levity allows the denser, heavier particles of gas around them to sink and come to rest gently upon the Earth, while pushing the lighter bodies aloft. This motion, over time, creates a great agitation in the atmosphere, by which means the air around us will slowly be warmed by the cooperation of radiation, conduction, and agitation. We have here an explanation of the equal diffusion of free caloric on a grand scale. Mrs. B encourages Caroline and Emily to observe this for themselves. You may perceive this effect on a sultry day. If you attentively observe the strata of air near the surface of the earth, they appear in constant agitation. For though it is true that air is itself invisible, yet the sun, shining on the vapors floating in it, render them visible like the amber dust in the water. The world, this is conclusion, kind of a long conclusion. The world around Marcet changed as quickly and alongside the changes in chemistry itself. As chemistry was better understood, it became useful, and the reasons for learning chemistry evolved. While Marcet acknowledges the usefulness of chemistry in the first edition, subsequent editions included ever more practical applications, discussions of the miner's lamp, the steam engine, and applications in agriculture. In a development that Marcet might not have anticipated, well, maybe she anticipated it, the applications of chemistry, as the applications of chemistry to industry expanded, the motivations for men and women to learn chemistry also diverged. Men's study of chemistry was more and more subordinated to the ways in which it could be used to harness nature's power for the purposes of industry and the accumulation of wealth, while women could continue to study chemistry as a part of natural philosophy and as a liberal art. In the United States, throughout much of the 19th century, women who were privileged enough to obtain advanced education often sought out education in natural philosophy, physics, botany, and chemistry. The men who were privileged enough to obtain advanced education studied Greek, Latin, theology, law, and mathematics. One sees the beginnings of these divisions in Marcet's life. If we contrast her work with her contemporaries, we can compare her work even to her husband's. Mrs. Marcet was married to a Genevan man who also studied chemistry, but who needed to pursue medical instruction in Scotland following his imprisonment after a sort of revolution that followed the French Revolution, a sort of smaller scale revolution. He was put in jail and then he needed to get out of town, so he went to Scotland and got a medical degree. Marcet continued to practice medicine until Mrs. Marcet's father died, leaving them enough money for him to pursue his own interest in chemistry. His interest was in biological chemistry, and he made some important discoveries about kidney stones. For much of his life, he actually unfortunately died quite young, Mr. Marcet spent his time visiting patients and no doubt collecting their urine. When he returned home and found spare time, he would study these urine samples, conducting various experiments on them. Mrs. Marcet, on the other hand, was free to study the latest journals and books, attend lectures, and arrange for the leading scientists to come to dinner, where she was rather well known for her avid interest and keen questions about their research. Her own research in the laboratory, led by a more wide-ranging philosophical inquiry, rather than the pressing needs of sick patients, was in many ways freer than Mr. Marcet's. If we compare Marcet's conversations with Samuel Park's Chemical Catechism, I think it's great that his book is called Chemical Catechism. That's the title of another textbook. It was the other leading chemistry textbook of the time. The portrait that we get of men learning chemistry contrasts with the portrait we get of women learning chemistry in much the same way that Mr. Marcet might be contrasted with Mrs. Marcet. Park's textbook begins with, quote, an essay on the utility of chemistry to the arts and manufactures addressed to parents in the higher and middle ranks of life, end quote. And here's the introduction. From the present state of chemical knowledge and the daily improvements which are making in our arts and manufactures by the judicious application of its principles, it has become absolutely necessary to make chemistry a regular branch of education, and that every youth should be acquainted with its rudiments, whether he be designed to move in the higher ranks of life or is likely to be concerned in any of the manufactures of the country. Parks then goes on for 24 pages on the utility of chemistry, covering everything from candles, paper, sugar, cotton, bleaching, and liquor. It is perhaps no accident that many of these uses will be applied to the raw materials that were now being harvested in abundance by enslaved persons in the United States. Parks makes a couple attempts at thinking through something beyond material interests, but he doesn't succeed. For example, he continues the above introduction by thinking about the theoretical uses of chemistry. It's an oxymoron he seems oblivious of. In doing this, he praises the theory of Archimedes before discovering the real value of such theoretical learning. Archimedes was enabled to invent such mechanical engines as were sufficient to resist the whole Roman army. For Parks, the value of theory is its use in the creation of mechanical engines of war. Later, he imagines a, quote, son born to opulence, end quote, a son whom we might imagine is enabled by reason of his opulence to pursue theoretical study without regard to its applications. But not for Parks. He turns instead to the fact that surely this heir has an extensive domain. I can't do justice to the utilitarian commercial crudeness of Parks' advertisement myself, so here he is. Quote, is your son born to opulence? Is he the heir to an extensive domain? Make him an analytical chemist, and you enable him to appreciate the real value of his estate and to turn every acre of it to the best account. Has he a barren tract of country which has been unproductive from generation to generation? He will explore its bowels with avidity for hidden treasures and will probably not explore it in vain. By analyzing the minerals which he discovers, he will ascertain with facility and exactness what proportion of metal they contain and which of them may be worked to profit. Thus he will operate on sure grounds and be prevented from engaging in expensive and unprofitable undertakings. Okay. In contrast, here is Caroline in her first remarks of Marcet's text. Caroline, to confess the truth, Mrs. B, I am not disposed to form a very favorable idea of chemistry. I prefer the sciences which exhibit nature on a grand scale to those which are confined to the minutiae of petty details. Can the studies which we have lately pursued, the general properties of matter, or the revolutions of the heavenly bodies, be compared to the mixing up of a few insignificant drugs? We can hear in Caroline's question a concern that the study of chemistry is a less philosophical way of studying nature. We can also see her concern that it is the sort of study that a shopkeeper or a tradesperson would do. Here is how Mrs. B responds. I rather imagine, my dear Caroline, that your want of taste for chemistry proceeds from the very limited idea you entertain of its object. You confine the chemistry's laboratory to the narrow precincts of the apothecary's and perfumer's shop, whilst it is subservient to an immense variety of other useful purposes. But besides, my dear, chemistry is by no means confined to works of art. Nature also has her laboratory, which is the universe, and there she is incessantly employed in chemical operations. You are surprised, Caroline, but I assure you that the most wonderful and the most interesting phenomena of nature are almost all of them produced by chemical powers. You may easily conceive, therefore, that without entering into the minute details of practical chemistry, a woman may obtain such a knowledge of the science as will not only throw an interest on the common occurrences of life, but will enlarge the sphere of her ideas and render the contemplation of nature a source of delightful instruction. When Marcet has Mrs. B, Caroline, and Emily begin work in the laboratory, they do not do so as doctors, manufacturers, or opulent boys with estates they anticipate avidly digging up. Their chemical pursuits are more free. While their chemical pursuits are free, Mrs. B guards against their abuse of this freedom. Their investigation follows a plan. Mrs. B insists upon it at regular intervals. For example, she informs the young woman that it would not be proper to investigate combustion before investigating heat, and that it would not be proper to investigate combined caloric before studying free caloric. In a discussion of vegetation in Volume 2, Caroline suggests that Mrs. B should have ended rather than begun their discussion with the 4 different kinds of fermentation. Mrs. B takes this under consideration and thoughtfully responds with her account. Had I begun with the germination of the seed, which at first view seems to be the most proper arrangement, I could not have explained the nature and fermentation of the seed, or have described the changes which manure must undergo in order to yield the vegetable elements, carbon, hydrogen, oxygen, and nitrogen. To understand the nature of germination, it is necessary, I think, previously to decompose the parent plant in order to become acquainted with the materials required for that purpose. I hope you will find that the order which I have adopted is in fact the best calculated for the elucidation of the subject. Here, Mrs. B emphasizes that the ordering of material is for the elucidation of the subject matter. It serves a pedagogical purpose. Elsewhere, in describing the progression of the material, she admits to a greater ambition. Faint and imperfect as are the ideas which our limited perceptions enable us to form of divine wisdom, still they cannot fail to inspire us with awe and admiration. What then would be our feelings were the complete system of nature at once displayed before us? So magnificent a scene would probably be too great for our limited and imperfect comprehension. And it is no doubt among the wide dispensations of providence to veil the splendor of a glory with which we should be overpowered. But it is well suited to the nature of a rational being to explore, step by step, the works of creation, to endeavor to connect them into harmonious systems, and, in a word, to trace the chain of beings, the kindred ties and benevolent design which unites its various links and secures its preservation. In her conversations on chemistry, Marcet might be undertaking just this, to display the complete system of chemical nature, endeavoring to connect the small chemical operations of nature into a whole harmonious system, to trace chains of being and discover kindred ties and benevolent designs. We might compare Marcet's undertaking to Mendeleev's first sketch of the periodic table. Both Marcet and Mendeleev are attempting to organize chemical knowledge. Mendeleev's ambition is in many ways smaller. He simply wants to arrange the known elements in a way that elucidates some of their most certain properties. He thus arranges them with an eye to weight and the proportions of chemical combination. While Marcet also orders and classifies the simple bodies, this starting point is fundamentally different for her. Mendeleev, I believed, hoped to create a table that would serve as a kind of deductive machine for both finding new elements and for anticipating their properties. Mendeleev was looking for a complete mastery of the elements, akin to the kind of mastery Newton effected of the heavens through a few laws of motion, geometry, and the deductive sciences of geometry and calculus. Marcet's contribution to the organization of chemical knowledge is not a table. It's a list of the conversations on chemistry and their subject matter. This is found at the beginning of the book in the table of contents. It has a fundamentally different but equally important character to Mendeleev's organization of elements. Marcet's method is not an attempt at mastery of elements, it is to place man in an ordered chemical cosmos. The patterns she is interested in are not those of weight or the tables of affinities or ratios of chemical combination. These patterns are of interest, but only as secondary to the organization of the world she knows. Her plan is to explore, step by step, the works of creation. Let's look at her list of conversations. In her first conversation, she says what chemistry is and how it should be distinguished from other forms of inquiry into nature. This introduction to chemistry is so influential that Mendeleev's introduction 60 years later sounds largely the same. An imitative text written by a Nobel Prize-winning physical chemist in 1905, also entitled Conversations on Chemistry, also sounds the same. Your high school textbook was likely a distant echo of this conversation. The next 4 conversations take up a discussion of light, heat, and electricity. Marcet thus groups together topics that are now studied as part of physical chemistry. While no chemist doubted the importance of heat to the study of chemistry, the inclusion of both light and electricity was not universal. A rough division emerged in the early 19th century between those who, admiring the success of Newtonian mechanics, wanted to reduce chemistry to physics, introducing no new causes, but reducing the strange interactions of matter to mass, inertial forces, and gravitational forces. The other branch, I didn't write that. The other branch is those people who thought that electricity was really important. This desire to reduce chemistry to physics is present in most, if not all, of the authors we currently read in freshman laboratory, including, as you might have guessed, Mendeleev. Oh, here it is. Marcet belonged to a different school of chemists, one who embraced the new researches in electricity and believed that the fundamental elements and the intimate relations between them were likely electrical in nature. As you might know, this school of chemistry, while it fell out of favor in the second half of the 19th century, came back with renewed vigor in the 20th. The remainder of Volume 1 is a close study of 6 elements: oxygen, nitrogen, hydrogen, sulfur, phosphorus, carbon, and then one class of elements, metals. Why did Marcet choose these particular simple bodies, and why metals? While she gives a modern classification of chemical elements in her first conversation, she seems to acknowledge the importance here of traditional ways of distinguishing matter: air, water, fire, and earth. Conversation 6 concerns the main elements of air. Conversation 7, the additional element required for water. Conversation 8, elements associated with fire, sulfur and phosphorus. And conversations 9 and 10 on the organic and inorganic elements of earth, carbon and metal. Here we see Marcet finessing the competing ways of understanding the subject matter of chemistry, inciting in an Aristotelian way with the thought that one should begin with what is first for us. Elements to the specialists might be a long list of unanalyzed simple bodies, but to the layperson, what matters is a rougher yet more philosophical classification. What is this substance that I breathe? What is water, so necessary for life and predominant in nature? What is fire, the source of light and heat? And what is earth, the source of bodily solidity and of heaviness? We have then, in the first volume introduction, a series of conversations on the new principles and agents of modern chemistry, light, heat, and electricity, and then a series of conversations on how modern chemistry explains the long-standing classification of matter into air, water, fire, and earth. The second volume begins with the nature of compounds and explanations for why and how elements come to combine. Here she explains the law of combinations of definite proportions, as well as Berthollet's observations about how the presence of heat and abundance of reactants sometimes change the proportions. She closes the chapter by decomposing a salt with the aid of a voltaic battery. She includes a variation at the close of this experiment, which seems to show that she anticipates the discovery that acids owe their acidity and alkalis their alkaline properties to the decomposition of water. But in typical Marcet fashion, she lines up the axes for an Odysseus rather than stringing the bow herself. The remainder of the second volume divides into discussions of alkalis, then earths and acids, before turning to a discussion of organic chemistry, which is divided into the chemistry of plants and animals. Here, as in the first volume, she is keenly aware of the way in which the ultimate simple bodies of chemical analysis are not always the elements appropriate to a given discussion. While she begins with an articulation of the importance of hydrogen, carbon, oxygen, nitrogen to plants, and hydrogen, carbon, oxygen, and to a greater degree than in plants nitrogen, as well as phosphorus in animal life, it is the more complex compounds that she turns to in order to explain the elementary substance of life. Just as air, water, fire, and earth are what is first for us in our understanding of the elementary substances of the world, so too the compounded substances prevalent in living bodies are important for our understanding of the chemistry of the living world. Sugars, oils, saps, fibrous matter, and the various organic acids, minerals, and proteins that make up blood, urine, milk, bones, muscles, and nerves. There are also analogous systems to consider. Just as the equal diffusion of heat and the crown of cups reveal the way in which caloric and electricity circulates through matter, she turns the cycles of fermentation and she turns to the cycles of fermentation and the circulation of sap to explain the heat of plants, and the respiration and circulation of blood to explain the heat of animals. After reading Marcet, what one gains is an understanding of chemistry that is nothing like that which our current textbooks give us. This is the chemistry of a world in which we live, about which we have questions, and without which we proceed blindly through our lives. In her preface, Marcet falsely claims that she has made no original contribution to chemistry. But through Mrs. B, we hear a less diffident chemist who shows Caroline and Emily around the laboratory and in an orderly way introduces them to the domain of chemistry. In this, I see a similarity between Marcet and Émilie du Châtelet. This is the woman who I think Emily's named after. This is a quote from Émilie du Châtelet. "Physics is an immense building that surpasses the powers of a single man. Some lay a stone there, while others build whole wings. But all must work on the solid foundations that have been laid for this edifice in the last century. There are still others who survey the plan of the building, and I among these latter." Like du Châtelet, Marcet might not be among those natural philosophers who will contribute a new finding, a stone here, nor a whole branch of chemistry, a west wing. If I were to develop du Châtelet's metaphor, I would describe Marcet as an architect. Unlike du Châtelet, she doesn't survey the plan of a building already built. She draws the architectural plans for how one might build chemistry. But rather than using du Châtelet's language, perhaps I should use Marcet's own. At the close of the 18th century, chemistry was breaking away from a long history of alchemical research and moving away from the ideas of transformation and towards the ideas of discovering principles and elements. It was disorderly, vibrant, but it was largely incoherent. Lavoisier, as the freshmen will soon read, tried to impose some order by insisting upon a common language and imposing many of the lessons learned from Newtonian mechanics. But there was more work to be done. Science was happening across continents, recorded in various journals. It was in notes of lectures, in books that were as likely to be alchemical as chemical, and in various other introductions to chemistry. Lavoisier, I think, was the one who taught chemistry to talk, but it is Marcet who showed the world what these conversations should be about.